in depth. So let's consider the following situation. So let A sub n be a sequence defined recursively by the following rule, that a n plus 1 is equal to a sub n plus 8 times n. So it tells you that to generate the next term in this sequence, you need to take the previous term and add to it 8 times the position n. And it's also given that the first term is equal to 1, so we can apply the recurrence relation many times and generate all the other terms in the sequence. So that's given. Prove by mathematical induction, so we'll shorten this to mi, that a sub n, the nth term in this sequence, is given by 2n minus 1 squared for all n greater or equal than 1. So we're supposed to prove that actually this recursively defined sequence can be also defined through this explicit formula for the nth term. So what is the statement we're going to be proving? The statement is here is that equality. So I write a column here, right? Because P of n is not going to be any part of that formula, right? It's the whole formula itself. A sub n equals 2n minus 1 squared. So base step, we pick the smallest integer n for which it is supposed to hold. And we're told it's supposed to hold for n greater or equal than 1. So for n equals 1, we take this statement and take the P of 1, which says that A1 equals 2 times 1 minus 1 squared. So that's 1 squared, that's 1. And that's true, because we were told that the first term in our sequence is 1. Okay, so base steps is really usually absolutely straightforward. Just substitute the number and check. Okay, on to the induction step. So now we assume that P of k is true for some n equals k. Okay, so what does it mean explicitly? So I replace n by k, so we assume, that is, we assume that a sub k is equal to 2k minus 1 squared for some k. Okay, so we assume this is true, therefore I can immediately label for myself that this we can use this. We can use this formula, right? And then we can write out what we're after. So we want to show that P of k plus 1 is true. So here, just replace k by k plus 1. So we want to show that a k plus 1 is equal to 2 times k plus 1 minus 1 squared. And here, I will put a question mark about this equality, not to get confused in terms of what is given and what we want to show. And also mark for myself that they want to prove this. So we're allowed to use this equality, the first one, And we want to use it somehow to show that this other equality with the question mark is correct. If we manage to do that, since k is arbitrary, right, that will be equivalent to showing, this implication in any position, right? And then by mathematical induction, the statement will be true for all values of n. So just looking at the equations, in the two equations, I see that, well, to get started with the second equation, well, I need something which involves ak plus 1. But the equation I can use only involves a sub k. So I need somehow to bring in ak plus 1. And then I recall that, besides this equation, I have my recurrence relation. That's given, right? Because that's, the definition of the sequence we are working with. So that's also given, was given from the start. So, to prove this statement, I'm going to start out with the left-hand side and use the recurrence relation. So by the recurrence relation, a k plus 1 is equal to a sub k plus h times k. Right? It's true that recurrence relation is true for any n, in particular for n equals k. So we can write that, and now I expressed ak plus 1 in terms of a sub k, and I know something about a sub k, right? Because I assume that formula is true. So the next step, I use my assumption. I use the P of k statement, right? So this is equal to 2k minus 1 squared plus 8k, and we can write to ourselves that this is by P of k being true, by our assumption. Okay? So, nice. Now I have an explicit expression which no longer has a sub k or ak plus 1. It looks like some quadratic polynomial in k, and the remaining step is a little bit of algebra, which I need to show that that expression wraps up in that square, because that's what I want to show. Sorry, here, this square, right? So that's what I want to show. Okay, so we can just expand them. Right, so this equals to, I start squaring it, 4k squared minus 4k plus 1 plus 8k. And this I can simplify. This equals to 4k squared plus 8k plus 1. So we can also expand the right-hand side of the formula we're trying to prove and compare it term by term, or equivalently, I can just notice that this is the same as the square of 2k. Yeah, 4, thank you. Thank you. Because minus 4k plus 8k, that's plus 4k, thank you. Yeah, just in time. So that's 2k plus 1 squared. Okay? Which is the same as the right-hand side there. And so this coincides with the right-hand side of P of k plus 1, which is 2k plus 1 minus 1 squared. Because if we expand this internal set of brackets, that gives us 2k plus 2 minus 1 squared, and that's the same as 2k plus 1 squared. Okay? So this thing is the same as that. Therefore, P of k plus 1 is true. Since we proved the base step, and k here was arbitrary, by mathematical induction, P of n is true for all n greater or equal than 1. Questions, please? Something not quite clear in this sequence. What I used, why I used that. Please, now is the time to ask. Yes, please. It is what? Oh, I mean, it doesn't matter which letter you use. I mean, so N or K, they're just conventional. It could be anything you like, as long as you're clear, you know, in using two different letters. So there's like, the role of N here is just an arbitrary label, like A1, A2, A3, so it's an arbitrary label. But K, we suppose it's some particular but unspecified value of n, okay, for which we assume the statement is true. It's a little bit confusing, right? The method is abstract. That's why it is hard to grasp. But that's where its power lies. Being abstract, it applies to lots of different situations. It necessarily has to be abstract. Okay. So let's do another example. And I'll follow the same template. Prove by mathematical induction that 2 to the power n is less than n factorial for all integers n greater or equal than 4. Okay. So now our P of n is an inequality. Right? So before we had certain equalities, now it's an inequality, which says that 2 to the power n is less than n factorial. And if you plug in a few numbers like n equals 1, 2, 3, you'll find that actually, no, that's wrong, right? For example, for n equals 1, I get 2 here, and 1 factorial is just 1, so it's wrong. But we're going to check that, at least for n equals to 4, this is already correct. So that's the statement we want to prove, right? It's an inequality now. And I start with the base step. And now the statement is supposed to be true for n greater or equal than 4. So the smallest value of n for which it is supposed to be true is 4. So I check, right, that it's true for n equals to 4. So I substitute into my inequality n equals 4. And on the left-hand side, I get 2 to the 4th power, which is also known as 16. And on the right-hand side, I get 4 factorial, which is 1 times 2 times 3 times 4, which is 24. And since 24 is greater than 16, that's indeed true. So P of 4 is true. Okay? So base step is done. Now on to the induction step. So here, again, if you don't know what to do, but you can always write out P of k and write out P of k plus 1, which is as easy as just substituting k for n and substituting k plus 1 for n, right? You can always do that. Then the first one will mark as the one we can use, and the second one will mark as the one we want to show, and then we'll stare at them and see what do we do next, right? But this step can always be done. So assume P of k is true, which means that 2 to the power k is less than k factorial. And I mark for myself that this can be used. Next, we want to show that p of k plus 1 is true. So what is this statement p of k plus 1? That's the statement that 2 to the power k plus 1 is less than k plus 1 factorial. And I put question mark above the inequality, right? I mark to myself that we want to show this. And nothing else is given, right? In the previous problem, we were also given the recurrence relation, and it was easy to forget about it, but here we have everything on the board. So somehow, from this first expression, first inequality, the second inequality must follow. Well, one other thing to keep in mind still is that k is supposed to be greater or equal than 3. Right? That's another piece of information which was, sorry, greater or equal than 4. So that was also given, right? Nothing else is given. So I'm going to start with the left-hand side of this formula I want to show. I'm going to use the index rule. So by index rule, 2 to the power k plus 1, that's the same as 2 to the power k times 2 to the first power, which is the same as 2 to the power k times 2. And why did I do this? Well, I know that that's the only formula I can use, the only inequality I can use. It contains 2 to the k, while what I have here is 2 to the k plus 1. So I have to do something to bring in some quantities which appear in the statement which I can use, right? And that's the kind of context-depending step, right? In the first example in the previous lecture, what we had to do, we had to realize that we have a sum of k plus 1 terms, and the first k terms are the same as in the statement we can use. In the first example here today, well, we had to use the recurrence relation, right? To get the quantity about which we know something. Here I have to use the index rule. Okay, so this is where the difficulty is, and the only way sort of to learn to do this is by practicing. So now that I have 2 to the k, I can use that inequality. So by p of k, this is less than k factorial times 2. Okay, we're making some progress. We already wrote one inequality, and the left-hand side is the one we want to have. So we need to move on, right? We need to arrive to the right-hand side, which has k plus 1 factorial. Okay, so how are k factorial and k plus 1 factorial related? So k plus 1 factorial is a product of all numbers, 1, 2, 3, and so on, with the last one being k plus 1. While k factorial is a product 1 times 2, 3, so on, with the last one being k. So k plus 1 factorial is actually k factorial times k plus 1. There's one more factor in its product, right? So I'd like to replace this 2 by k plus 1, and then I'll be in business, because k factorial times k plus 1 will be k plus 1 factorial. And actually, I can do this because 2 will be less than k plus 1 when k is greater or equal than 4, because k plus 1 is at least 5. So this step is true because k is greater or equal than 4. So I leave the first factor as is, k factorial remains k factorial, but I replace the second factor 2 by a larger factor, k plus 1, because k plus 1 is at least 5, greater than 2. Okay? And this is the same as k plus 1 factorial. So we did 2 inequalities here, right? But always in the same direction, always in the larger direction. So the 2 to the k plus 1 is smaller than this expression, and this expression is smaller than k plus 1 factorial. Well, then therefore the extreme part, the leftmost part, 2 to the k plus 1, is smaller than the rightmost part, k plus 1 factorial. And therefore, so this means that P of k plus 1 is true, and by mathematical induction, P of n is true for all n greater or equal than 4. Okay. Questions, please? Yes. Maybe first.
Can you explain the k plus 1 part again?
Yeah. So I replaced 2 by k plus 1 because k plus 1 is bigger than 2. K is at least greater or equal than 4. So k plus 1 is at least 5. That's bigger than 2.
Yeah.
So this is correct. So this is smaller, that is bigger.
Why do you not treat k as true?
Well, it's always true. And we know, we checked explicitly that P of 4 is true. So for some case, we definitely know that it is true. But because we don't specify the k, we don't specify the value of k here, so it can be anything. So if P of 4 is true, then what this second step shows that P of 5 must be true. Knowing that P of 5 is true, this step again, used again, implies that P of 6 is true, and so on. So by not specifying k, so why are we doing it? Because this is how the method works. Right? You assume that something, this is an honest implication. Assuming that the first formula is true, we show that the second formula is true. How is that being used? Why does this imply that it works for all n's? Because there's the base step. Because there is at least one value for which we checked explicitly that it is true. And that is enough to get us started, that we could use this implication again and again. Does this help? Well, if you're on the exam, if you're asked to prove by using mathematical induction, then it won't be okay, because you did something else, right? I mean, you don't like it, I understand, but you know, there are situations when you cannot really prove without it. So, and it's a really very widely used method in discrete maths, and it's the only place in the whole course where, yeah, you have to suffer with proofs. Okay, but it's just because it has such a prominent position in discrete maths that we're studying this. And the main idea is, of course, not to become proficient in applying it left and right, but really to grasp how it works. And the only way to grasp how it works is by doing such elementary examples of this type, right? So I have, in addition to the examples in the type notes, to think pretty much like the ones I covered on the lectures, there is another file on Vision which has more fully worked examples on mathematical induction. Yes?
Why do we multiply factorial of k by 2? Is it to prove that we multiply it by the same?
We did multiply it by 2.
Yeah.
2 is kept here the way it is, and I use this inequality because this inequality says that 2 to the k is less than k factorial. So 2 to the k was replaced by a bigger quantity k factorial.
So we do it to give that
No, we're using inequality. So if you have two factors, a times b, and a happens to be less than c, then multiply both sides by b, and you get ab is less than cb, right? So I kept one factor as it is, but the other one I replaced by a bigger quantity. And it's sort of, you cannot possibly come up with any other move here, right? Because the only thing I know is this, right? So I have to somehow use that. So you're really led to this step. Okay? Okay. It is tricky, but right. The only way I think to learn it is really by working through examples. So on the tutorials next week, that's what we will be doing, right? And also I would recommend to read the additional examples on vision. Yes, please.
Paper.
Yeah. Here. Yes. Yes? Okay, so you're suggesting to replace, keep 2 as it is, but replace k factorial by k plus 1 factorial. Yeah, but then it will be less than 2 times k plus 1 factorial, which is an overshoot. No, that's not good. You can't go back, because what you suggest would show that 2 to the k plus 1 is less than 2 times k plus 1 factorial. But what you want to show, yeah? Sorry? Greater, but it's in another direction. What do you mean allowed? I mean, you're allowed to use any legitimate inequalities. So that's, I mean, you cannot conclude from these that 2 to the k plus 1 is less than k plus 1 factorial. Because k plus 1 factorial is somewhere in between, it's smaller. If you have something here like that, then you can conclude that the leftmost part is smaller than the rightmost part. But that's not going to help you here. So it is true, but it doesn't lead you to the result we want to show. So it's a correct inequality, but that's the wrong step to do because it doesn't lead to the correct inequality. Yes, please. What? Factorial. Yes. I defined it when I spoke about functions. Okay? Any other questions? Okay. Then I have to switch gears again because we have a lot of material to cover. So I'm going to start talking about combinatorics. Right, so combinatorics is a branch of mathematics which is concerned with counting. So you can be counting, generally speaking, processes. In how many ways a certain thing can be done. Or you can rephrase it and say you'll be counting elements in a certain set for which some specific complicated probably rule can be formulated, which tells you which elements are in it. So it's not such a straightforward question. And it's a very important part in discrete mathematics in particular in terms of applications to computing, because very often in computing you want to estimate sizes of data or running time for various algorithms, right? And then then you use the methods from combinatorics, and it's a very important step to kind of get the feel for how feasible your algorithm is, or how fast your program will be running. So I'll start with the most elementary counting rules. So one of them is called the sum rule, and another one is called the product rule. And for the sum rule, I'll start with the following motivating example. So, these examples are very artificial. Very often it's about some committees and selecting people for committees. So it's kind of historically that's what you find in books. So a teaching committee requires one student representative from either the first or the second or the third year. And there are 500 first-year students, 300 second-year, 100 third-year students. How many possible different committees are there? So a teaching committee requires one student representative who can be from either the first or the second or the third year student. There are 500 first year students, 300 second year students, and 100 third year students. Only the toughest survive. So, how many possible different student representatives are there? Well, we can choose any of the 500 first-year students, or we can choose any of the 300 second-year students. This gives us 300 independent choices, so we'll just add them. And finally, we can also choose any one of the third-year students, and there are 100 choices there. And we just add up these choices to obtain the final answer, 900. So what was crucial here is that in adding up the choices, we should make sure we never double count or triple count. In other words, we never overcount our choices. But that is guaranteed by the following fact that none of the students can be simultaneously, say, first and second year, or second and third year, right? Each student only belongs to one of these three sets. And then we can just add up our choices. So we can generalize now this example to more generally to a general rule, which is called the sum rule, which says that if there are n of a ways to do A, and distinct from them n of b ways to do B, then the number of ways to do A or B or B is n of A plus n of B. And so the important words here are distinct from them. That's the same condition as that we used in the previous example when arguing that we're not overcounting, because any student in the first year is distinct from a student in the second year or the third year. Okay? Then we can simply add our choices when we're answering this question, the number of ways to do A or B. So this or, right, tells you when you can apply this rule, this type of counting problem. Count the number of ways to do A or B. Also note that this rule can be applied several number of times. Essentially, so here we have only A and B, but you can iterate it and apply the situations when you're counting the number of ways to do A or B or C, as long as they're all pairwise distinct. And you don't have to stop at 3 sets, can be as many sets as you wish. So it generalizes to any number of sets or processes. Right? If they're all pairwise distinct, then we can simply add up the choices. Okay, let's look at another example. Now, a committee is composed of 3 students, and one student has to be from the first year students, the second student from the second year students, and the third from the third year students. Okay, here's another example. A committee is composed of 3 students, one from first year, one from second year, and one from a third year. Right? Well, assuming that the numbers for first, second, and third year are the same, namely 500 here, 300 for the second year, and 100 for the first year, how many possible different committees are there? So how many possible different committees are there? So now you can easily distinct the processes. A, we can call A is the choice of the first year representative, and B can be the choice of the second year representative, and 3 is the choice of the third year representative. And it's not that we have to choose either one of them, but we have to choose all 3 of them. We have to choose the first year representative, and we have to choose the second year representative and the third year representative. It's a different type of counting question. And we can think in the following way. So we have 500 choices for choosing the first year representative. Now, once that representative is chosen, and for each one of them, I have 300 choices to choose the second year representative. Therefore, I have to multiply, right? Because each one of these 500 comes with 300 choices for the second year representative, right? Once I have chosen the first year rep and the second year rep, I have still to choose, for each pair here, I have to choose the third year rep. And I have 100 choices. So each pair here comes with 100 choices for the third year rep. So I have to multiply the number of pairs by 100. So that is the final number, the final answer for this problem. So this is 15 million different possible committees. And we can now generalize this to the following rule, which is called the product rule. And it's formulated like this in the simplest case. If there are n of a ways to do A, n of a ways to do A, n of b ways do B, then the number of ways to do A and B do A and B is n of A times n of B. Just multiply these choices. So note this and here, right? It tells you what type of counting question this applies to. So in the previous it was to do A or B. Now in this rule you have to do A and B, right? You have to choose the first year representative, and you have to choose the second year representative for your committee. And just like in the previous case, you can iterate it and apply this product rule several times, so that, for example, if you have 3 sets, so this generalizes to 3 or more processes. Right? And the rule is that if you have to do A and B and C, so for example, the number of ways to do A and B and C is n of A times n of B times n of C. And it is, of course, assumed that each choice is independent. So you, having chosen a way to do A, should not affect your choices to do B. Okay, so that's, again, there is some assumption here. So let's write this down. It is assumed that any choice does not affect choices for other processes. Okay. All right. So let me do a few more examples. I'll show you an example when both counting rules will be used. Okay, let's consider the following problem. In a certain computer system, a file name must be a string of letters or digits, which is 1, 2, or 3 symbols long. So what we've got a file name must be a string of letters or digits, which is 1, 2, or 3 symbols long. So the first symbol must always be a letter. The first symbol must always be a letter. And the system does not distinguish. So let's say letters are always lowercase. How many different legitimate file names are in this system? How many different legitimate file names are in this system? Okay, So what do we have to count? We have to count all possible file names. And at first I see three distinct possibilities. So each file name is either one symbol long or two symbols long or three symbols long. And these are three distinct possibilities. Right, so there's no overlap. There's no file name which is simultaneously one symbol long and two symbols long. That's nonsense, right? So there's three distinct possibilities, and either one of them is allowed. So this immediately tells you that you can use the sum rule. So we can separately calculate. So we can separately calculate the numbers for each length. And then apply the sum rule. Okay, so let's do that. For those file names which are one symbol long, well, we know that the first symbol, which is here the only one, must always be a letter, a lowercase letter, and there are 26 letters in the English alphabet, so there are 26 names. Now, for two symbol names, I have to choose the first symbol and I have to choose the second symbol. Both choices are independent. Regardless of what I chose for the first symbol, I still have the same number of choices for the second symbol. So here we're going to use the product rule. That's the case where I have to choose the first symbol and I have to choose the second symbol. So by product rule, I have 26 choices for the first symbol, and so how many choices I have for the second symbol? It's the sum rule, because it can be either a letter or a digit. There are 26 letters and 10 digits, right? 0 is always considered to be a digit. So digits are 0, 1 through 9. Okay, so that's yet again sum rule. Using it again. And that gives me 26 times 36 choices. So 26 times 36, which is 936. Right? These are all possible two-symbol file names. Finally, for three-symbol file names, I use the product rule again, because I have to choose the first symbol, and I have to choose the second symbol and the third symbol. And I have 26 choices for the first symbol, 36 for the second, and 36 for the third. Because in the second and third position it can be either a letter or a digit. And using a calculator, that gives me 33,696. The final step, to add up the numbers for each length. So finally, by the sum rule, the number of all possible file names is 26 plus 936 plus 33,696, which you can find to be 34,658. Okay. So in this example, we used both sum and product rule many times in various places. Yes. 10, the digits. The digits. There are 10 digits from 0 through 9. 10 possible digits, right? 26 letters and 10 digits.